Well, good day everyone. In this video tonight we want to look at the design of a two-stage RC coupled amplifier. And before I go into this, let me quickly use this period to appreciate every one of you that have been watching, that have been clicking, that have been liking my videos, that have been sharing and recommending my videos. I appreciate you all. You guys are so important to me, and that is why I've always been taking it upon myself to put interesting videos every day in order to get you guys watching something very significant in the field of electrical and electronics engineering. So we want to look at how we design two-stage RC coupled amplifier. Now, why do we need a two-stage amplifier? Number one is that at times one-stage amplification might not be enough. For example, you may have a very low signal that need to be picked up by a low level amplifier, amplified it to a certain level before a high level amplifier will now pick it up. So in that case, you will need, definitely you are going to need more than one stage amplification. For example, when you have ECG say a signal, electrocardiograph signals, it's a very low signal that is like a heartbeat, pulse beat. So it needs to be amplified first to a level that can be picked with other bigger gadgets. So we want to look at how that is done using a two transistor amplifier. Like now, the point to note in this two-stage amplification is, number one, the total gain of a two-stage amplifier is equal to the product of the individual gain of each stage. The total gain of the two amplifier becomes the overall, as in the multiplication of each gains, the product of each gains. For example, this is a single stage amplifier represented in the block diagram. This is the input and this represents our output. So when you now have two stage, this becomes the input, this is the output, then this output becomes the input to the second amplifier to give us a better amplified signal. Now, one thing we must take note in these amplifiers we have been dealing with in the past videos, like the videos I did on a common emitter transistor amplifier implementation, you see that there are certain peculiar things about their waveform. And what is that peculiar thing? The waveforms are displaced by 180 degree. That is, the trough of one waveform is falling on the crest of the other. If you look at these two waveforms, you discover that when this one is going up, this one is going down. When this one is coming down, this one is going up. So that is why, that is to say, the waveforms are displaced by 180 electrical degree. But to audio amplifiers and other low level signals, this is not a problem. As far as the signals, the voice can be clearly picked. It does not matter the waveforms. What matter is the amplification. So another thing to notice in this two-stage amplification, the second stage amplifier, that is the second transistor, and all its attached parameters, the biasing resistors, the RC coupled and all those things, they become a load to the first stage amplifier. So once the second stage is added, its input impedance, the input impedance of the second stage amplifier, becomes an additional load to the first transistor amplifier, so thereby reducing the gain as compared to its no load gain. That is, when you have a single stage amplifier separated and you measure the gain, the gain could be like, let's say 4, for example. By the time you connect them in two stage and you try to measure the gain of one individual, and this is that first stage amplifier, you will find out one interesting thing, that the gain is no longer up to 4, because it is now seeing the second amplifier circuit as a load to its own input, to its own output. So part of the power generated, part of the voltage generated will be used to overcome the load of the second stage. So that is that about that. But one thing is, the loading effect decreases with frequency. That is, the higher the frequency, the lower the loading effect, and eventually at a very high frequency, this loading effect dies off naturally. So one way to overcome this particular challenge mentioned here is to increase the frequency of the input signal. If you can increase the frequency of the input signal, then the loading effect will cancel. So we're going to make use of the transistor circuit that we have developed in our previous video, that is common emitter transistor amplifier implementation. So I'm going to open that Proteus file, then we simulate it and see everything we have been talking about. So if you are familiar with if you have been following us all this while, you will find out this is the circuit we work on the other time. This is we've taken ourselves through how we arrive at these particular values for these biasing resistors. Remember, I did mention that this type of biasing is called potential dependent biasing method, and we took ourselves through how we calculate this value of R1, R2, RC, and RE. So now what I did is I just tried to find I just duplicated this circuit. So it's the same thing here. The same value that I put here is what I put here, because the parameters, what I want is I want the amplifier to have equal gain. So now the only thing I've added is I've now added another circuit. So let me separate this circuit now so that we measure the amplifier gain. So let me separate this circuit now. I want to separate this circuit, so we are only measuring these two gain, that is the inputs to the amplifier. Then we want to measure the output of the amplifier. So let's click and let's run the simulation. I want to take one shot. Now this is our input and the output waveform. Now if you look at, like what I said earlier on, let me try to increase this signal. Let me increase this signal so that you'll be able to see something. If you look at these two waveforms, you will find out that it's an antiphase of the other. You see, the crest of one waveform is falling on the trough of the second one. This is a classical case of a class A amplifier. So it's a classical case of a class A amplifier. So let's try to measure them individually. So this is the input signal, and each box on the input signal represents 1 volt from the channel, that is, we connected the input signal to channel A. So let's try to measure the input signal so that we can ascertain the gain. So from what is here, you can see that the input signal is sitting on one box alone. It's sitting on one box, and we have said from this channel setting, one box is equal to 1 volt, which means if that should be the case, our input voltage is 1 multiplied by 1, which is 1 volt. That's for the first stage amplifier. So we want to try to find the gain. So the output now of the first amplifier, let's try to find the output. This is the output. So let's try to measure it. So let's try to measure this output. Let me take these guys down so I can be able to centralize. I can be able to center this waveform. So let me bring it to the fore. Okay, I think everyone can see, right? So now I want to measure this. Let's try to make it in one box. Okay, so this is how many boxes? 1, 2, 3, 4. So this one is sitting on 4 boxes. 4, then each box equally represents 1 volt. So it means 4 boxes multiplied by 1 volt will give us 4 volts. So which means our output is 4 volt. So our output is 4 volt, our input is 1 volt. So the voltage gain of the first stage will now be 4 divided by 1, which will give us 4. So this is the voltage gain of the first stage of the amplifier. Okay, so let's try to stop the simulation and connect the second stage of the amplifier. Don't forget to connect the ground. Both of them will share the ground, and don't forget to connect the biasing voltage, because the second transistor need to be biased as well. So they are sharing everything now in parallel. So let me now measure the output, the overall output. So the overall output of the system will be measured from this. So we can simulate now. Let's try to simulate. Let's take a shot. So we now have how many waveforms on the screen? We now have 3 different waveforms on the screen. We have 3 waveforms. So the third one, this is the final waveform. So let's try to make all, okay, both of them are 1 volt, 1 volt for the yellow, 1 volt for the green, 1 volt for the blue. So the yellow, as we already know, is standing for our input signal, that is the low level audio signal, so which is standing on one box multiplied by 1, that is 1 volt. That's for the second stage now. I mean, that's the input to the first stage. Then the output of the first stage amplifier, the output of the first stage amplifier, let's try to measure it, is standing on how many boxes? Standing on how many boxes? 1, 2. Standing on 1, 2, 3. 3. Standing on how many boxes? Okay, let's count. 1, 2, 3. That's 3. So when you look at it, you see something has happened. So the output becomes 3. So let's, the second stage now, the output of the first stage, I mean the output has reduced to now, when that is when you are we have now connected it in there. This is when it was single stage alone, single stage unloaded. So this was the gain. Now for the second stage, V1 is still 1 volt, 1 volt. Then V2 is now 3. V2 is now 3 volt. We have seen that there is a reduction in gain. V2 has reduced to 3. 1, 2, 3. There's a reduction in gain. There's a reduction in our gain now. Then V3, which is the output of the second stage. V3. Let's measure V3 now. The output of the second stage amplifier is now. So let's count. Let's count. That's a 1, 2, 3, 4, 5, 6, 7. Let's count again. 1, 2, 3, 4, 5, 6, 7. 7 multiplied by 1 is 7, right? 7 multiplied by 1 is 7. Each of them is 1, 1, 1. So the V3 is equal to 7. So which means now the first gain is now what? So the overall gain will now be A1 multiplied by A2. So A1, which is the V1, A1 is what? V2 divided by V1, which is equal to 3 divided by 1, which is equal to 3. So then the second gain, A2, is now 7 V3 divided by V2. V2 becomes the input to that one, which is 7 divided by 3. So 7 divided by 3, that should give us 7 divided by 3. 7 divided by 3. 7 divided by 3 that will give us 2.3. 2.3. So the second gain is 2.3. Then the overall gain is 2.3 multiplied by 3, which will give us 2.3 multiplied by 3, 2.3 multiplied by 3, which is 6.9, approximately 7. So the overall gain is now 6.99, which is 7 approximately. So we have seen how the gain is affected. The gain of the first stage amplifier is affected because of the loading effect. And when you look at it, you see that the effect of the capacitors is being manifested here. The capacitive effect is manifesting here. But at high frequency, you know what happens at high frequency is that the capacitor become a short circuit. So in effect, capacitor will just be a piece of wire with zero resistance. So you won't see all this clipping. You know, when you look at this, you see voltage clipping, like the edge of the waveform is clipped, because you know we use capacitor to clip the edge or to trim the edge of signals. That's why they use capacitor in clipper circuit. But at high frequency, this becomes a normal thing. The circuit works well at high frequency. So this is how we do two-stage transistor amplifier, and that will be the end of this video. I want to thank you so much for watching and for subscribing to my YouTube channel, and for liking these videos, liking my previous videos. Please, if you have any questions, any complaint, any contributions, please kindly reach out to me. You can reach out to me by my comment section, or you can reach out to me by my personal email that is attached to this particular YouTube page. Please kindly share this page, recommend this page to your friends, your neighbors, to your course mates, your colleagues, for as many that are enthusiasts or passionate about electrical and electronics engineering. I appreciate your comment. I appreciate your time. Thank you for watching, and that will be all for now. So see you in my next video.